Students, welcome to the third and final video for topic 11.1, electromagnetic induction. This is, I think, by far the most complicated video. This is one of the most complicated and probably most difficult topics in all of IB physics. So you're going to want to really pay attention very carefully to this video. I'll do the best I can in explaining this to you, not in person. And of course, our time together spent in class will greatly augment what I'm talking about in this particular video. Okay. Now remember, we talked about Faraday's law, and we said that phi, which was just the magnetic flux through a cross-sectional area, was given by n times b times a. Okay. Cosine theta, the cosine theta comes from that dot product right there. Remember that? We talked about the n hat vector being the perpendicular vector to the area, thereby giving area direction. Okay, and then we had this discussion where we pushed the rod with a particular force resulting in a constant velocity from left to right in this case, and we saw that in this case we sort of derived Faraday's law by considering a case where the area was increasing. Remember, the area started off small here and it increased, and we did some mathematical tricks where we talked about the distance that the rod traveled being in terms of the speed and all this kind of thing. All right. Now, for a constant speed, if the speed is constant, it means that the magnetic field, okay, to the left, and remember there is a magnetic field. There is a magnetic field created by the current in the wire. Okay, the magnetic force to the left is equal to the force at which it's being pushed. Remember, I said a rod is being pushed by a force. Okay, and the question that we've been avoiding for some time is that in what direction does the current move? Okay, how do we know in what direction the current moves? And I'm going to have a discussion about the conventional current here in this video. Okay. Okay, you have a 50-50 chance. It's either clockwise or it's counterclockwise, okay? Now, we said that Faraday's law had that negative sign in there, and I said, don't worry about this, we'll talk about it later. Well, later is now. This is when I'm going to talk about it, okay? Said that the potential difference, or the induced EMF, is negative n d phi by dt, and that is BVL across the ends of the rod, okay? However, this is where it gets kind of funky and kind of complicated. The induced EMF itself creates an induced B field through the current it creates, right? So remember, for example, if I have the current moving upwards here, if the current is going up, which is the bottom choice right here, I would have an induced B field that actually comes out of the paper to the left and goes into the paper on the right, okay? All right, and that B field, the B field that is created by the current, which itself is created by the relative movement between the rod and the B field, that current itself creates a magnetic field, and we can determine the direction of that magnetic field. It's a radial field, which was determined by the very first application. Remember that thumb rule I told you guys about, where your thumb points in the direction of the current, and then your fingers curl around in the direction of the B field, okay? That B field is totally independent of the original B field. It does not have anything to do with it, at least directly. So the big question then is, in what direction does the conventional current move? Okay, turns out it depends on the polarity of the induced EMF. Okay, and by polarity I mean obviously which end is plus and which end is minus. So there are two possibilities. Okay, all right, and I'm going to define for you something called Lenz's law. And Lenz's law says that the induced EMF from a changing magnetic flux has a polarity. Okay, meaning that the induced current has a direction, which is such that the induced B field opposes the original flux change. And you'll see in this video that that's the way it has to be. There is no other way that it can be, okay? And this is why Faraday's law has that negative sign, which I've been avoiding addressing until now, okay? All right, and it can get complicated. Now, to determine the polarity of the induced EMF and therefore the induced current using Lenz's law, there's sort of a set of steps you can go through, but really it's just a matter of doing problems and getting an intuitive feel for it. Number one, determine whether the change in flux, remember it's not the flux in Faraday's law, it's the change in flux that is important. Determine whether the change in flux from the original B field is increasing or decreasing, okay? And that's usually pretty straightforward, okay? Find out what the direction of the induced B field is in order so that it can oppose the change in flux, okay? In other words, if your flux is decreasing, the induced B field must be to be opposite direction of the original B field, because it then has to serve to increase the original flux change. All right, we'll do examples of this, so don't worry about that. By adding to or subtracting from the original field. And once you found the direction of the induced B field, use the right-hand rule to determine the direction of the induced current. And remember, we're going to use a conventional current here. Keep things simple. It's fairly easy if you keep these three things in mind. Okay, so back to that example that we did of the sliding rod on the conducting rails. Okay, I'm going to call, because I'm dealing with two magnetic fields, I'm gonna differentiate them. I'm going to call the original B field, in this case, which is going into the plane of the paper here, I'm going to call it B1, and the induced will be B2. Okay, all right. I'm letting phi 1 be the original flux from B1, which is creating the current. Now, phi 1 in this case is increasing. How come? Because the area, the cross-sectional area is increasing, okay? So as time goes by, there are more field lines going through that closed loop than there were before, so it's increasing. Phi 2 is the induced flux, okay? And that's the flux from the current, okay, from the induced B field created by the current, which is created by phi 1. And again, the only reason why there's an induced flux and an induced current and an induced B field is because there's a change in flux by Faraday's law. So the total flux is just the sum of phi 1 and phi 2. Okay, you get that? All right. Case 1, let's consider that the induced flux, or the induced B field, is in the same direction as the original. Okay? All right, so my induced B field would be, if my current is down in that area, okay, that means that it would be the B field, the induced B field would be into the board like this. You want to test that, okay? Now, if that's the case, phi 1 and phi 2 are the same sign, okay? So the original flux, right, and the new flux are in the same direction, the same sign. So therefore, phi total would be greater than either one of them, okay? So phi 2 would add to the original flux change, phi 1. Get it? Okay? So it would actually make the change in flux, the original change in flux, greater. But this is not possible, because that acceleration would increase infinitely. The acceleration on the rod would increase infinitely, because the force on the rod would get bigger with no limit. Okay, if you remember, how is the rod moving, right? Remember the balance between the force and the magnetic force, okay? The force on the rod would get bigger with no limit. This would be impossible. So there's only one other choice. I'm going to show you why it has to be case 2, okay? Case 2, if the current is going in this direction, in this rod, if it's going upwards, okay, using your thumb rule here, you can see that the induced B field would then be outwards, okay? It's in the opposite direction. Phi 1 and phi 2 are opposite signs. Therefore, their sum is smaller. Notice that I have a negative sign on phi 2 because it's in the opposite direction. So phi 2 takes away from the original flux change, phi 1. By Lenz's law, it has to be case 2, which is the green case here. Okay, we're going to talk a little bit more about that. If you want to pause the video and look at this very important slide for a minute, I definitely encourage you to do that. Okay. Now, what if the rod were pushed to the left? Okay, so if it started over here and then went in this case, right? Now, would the induced current be case 1 clockwise or case 2 counterclockwise? Okay. In this situation, it would still be case 2, because since delta phi is negative, it's a decreasing area, then B2 must oppose that negative change in flux by adding to the original B1. Okay. Remember, use your thumb rule. Okay. The induced B field, very important note here. I should actually have this bright flashing red coming out at you. The induced B field is not always opposite to the external B field. It depends on how the original flux is changing. Okay, so I have 3 cases here. This is from the Cutnell and Johnson textbook. Okay, 3 cases. Which is correct, B or C? Okay, first of all, I have a closed loop here, magnetic field lines. This magnet is being moved towards this. Okay, so what is happening? First of all, is there flux? Definitely. The field lines that go through the cross-sectional area. Okay. As this magnet is moved towards that cross-sectional area, does the flux increase or decrease? Well, it's increasing, right? Because there's a stronger field. There's more field lines going through, okay? Now, if there's more field lines going through, then delta phi is positive. Therefore, we need an induced B field that opposes that original change, okay? All right? The only way that that's going to happen is if you have a situation like this. So the induced current has to be as shown in this diagram. Notice that if it's in the direction of B, okay, there will be an infinite acceleration because there will be infinite force applied, okay? All right, really cool topic, huh? This is one of my favorite topics in physics. I love talking about it. So if you guys have any questions about it, we'll do lots of examples in class. We'll be using right-hand rules and all kinds of crazy stuff. This is what I like about this topic, is that it really causes you to think outside the box and think really abstractly, but it's not that abstract because it's reality and it's actually all around us, okay? Try this example. A loop of wire has its plane horizontal, and a bar magnet drops from above so that it falls through the loop with the north pole first and the south pole first. Find the direction of the current induced in each case. All right, when it's entering the loop with the north pole down, okay, obviously the flux is increasing. Not only that, but the change in flux itself is increasing positively. Therefore, it's a clockwise current because the current has to create a B field that opposes that positive change. With the south pole down, it's just the opposite. Now, when it's exiting the loop, okay, even though I ask, do I ask about exiting? I don't think I do directly. Anyway, when it exits, it's just the opposite. Okay, with the north pole down, it's a clockwise current. With the south pole down, it's a counterclockwise current. Study this problem very carefully. You are now officially responsible for dealing with these kinds of problems. And you should be, as a higher level student, be able to handle a problem where you, because the magnet is in free fall, you know its acceleration, and you know how fast it's going, and you know the rate of change of its velocity. There's all kinds of devious questions we could ask you about this now, okay? Good stuff, okay? Another great example, okay? There's a constant B field in example 9, okay? Copper ring slides through the region. Okay, first of all, let me ask you guys, just stand back and think about it holistically. Which quantity is changing that would even produce a change in flux? Is it N? No, because it's one ring. Is it B? No, they're saying it's constant, okay? Is it theta? No, because everything's orthogonal. It must be A. This is a case where the area is changing, okay? Now, it looks initially like the area of nothing is changing, but due to the relative motion of the ring in the B field, the area of the magnetic field that is going through the loop itself is changing, but only as the loop enters the field and as the loop exits the field. Here, there is no change in flux. Here, there is no change in flux. Here, there is no change in flux. It's only when it's entering and exiting the field, okay? All right, so I'm asking you to sketch the direction of the induced current at each position and explain your reasoning briefly, okay? Okay. I'm saying 1, 3, and 5, there's no change in flux through the loop, so there's no current, as I just discussed. In position 1, the flux is increasing, right? Because there are more magnetic field lines going through the plane of the loop each instant of time because the loop is moving into the field, okay? Therefore, the current must be counterclockwise in order to oppose this change in flux, okay? In position 4, it's just the opposite. So you see, instead of freaking out about Lenz's law, what you really want to do is pause, think very rationally. You need to be focused, undistracted, so that you can really think about the way these things are working, okay? All right, the final slide. As a guitar player, I have to throw this in, okay? Really interesting application of induction in sound reproduction. If you've ever played an electric guitar, you know that it has pickups. And if you spend a lot of time noodling around with an electric guitar, you notice that the pickups have pretty strong magnets in them. Why do they have magnets, okay? Well, guitar strings are made from a magnetizable material. What I mean is it's a material where its magnetic domains are able to be aligned and actually become a magnet, at least temporarily. The pickup is a coil of a wire with a permanent magnet in it. The magnetic field of the magnet penetrates the guitar string. Okay, so you can see how the field lines would go up in this case. Okay, therefore creating all these little magnetic domains along the cross section of the wire oriented north-south like that. Okay. So that B field causes these domains to line up and it causes the guitar string to become magnetized vertically. When the magnetized string is plucked, it oscillates. And what it does is that oscillation then changes the magnetic flux that passes through the coil, because you in effect have a guitar string which is a magnet which is moving up and down at a particular frequency, right? This changing flux induces an EMF in the coil, and the polarity of the EMF reverses, it alternates exactly with the vibration of the string. So a string vibrating at 440 hertz, for example, it induces a 440 hertz AC potential difference in the coil. That signal is then amplified and sent to loudspeakers, and what comes out of the loudspeakers? A tone, a sound which is exactly 440 hertz. And that is how electric guitars work.